Today we're going to look at an important concept in groups, the idea of a homomorphism. So we're going to look at a homomorphism So what is a homomorphism? A homomorphism is a function, but we usually use the word, for some reason, abstract function we think about in analysis. Algebra, they often use the term mapping, but mapping function means the same thing. So it's a function that preserves the group operation. So specifically, it's usually we use phi from G to H, where G and H are groups so phi is a mapping, which again is interchangeable with the word function. Such that if we take any two elements, say G and G prime in G, if we look at phi of G times G prime, that's the same as phi of G times phi of G prime. And we actually have two, depending on the group structure. This multiplication here is multiplication within G of group elements. This multiplication here is phi of G is in H, phi of G prime is in H, so this multiplication is multiplication in H. So even though the notation looks the same, this multiplication here of these two elements of G on the left-hand side, on the right-hand side we have multiplication of two elements of H. So let's look at some basic facts. This is sort of a lemma. Let phi going from G to H be a group homomorphism. With E sub G, the identity of G, and E sub H, the identity of H. Then if we stick E sub G into mapping, a function, the input, the output is just the identity. In other words, any homomorphism will map the identity of G to the identity of H. So proof, take any y in H, actually, let's be a little bit more careful. So what we have is maybe we have let x be in G and let the output phi of x be y. Then if we look at y times phi of the identity of G, that's equal to, well, y is just phi of x times phi of E sub G by the property, but preserves multiplication. So rather than plug into the function and then multiply, that's equivalent to first multiplying and then plug in the function. But what do we know about the identity in G? X times E is just y. Oh, sorry. X times E of G is just x, so we have phi of x, and that's equal to y. And certainly y is equal to the y times E of h, and that does it, right? So canceling y on the left, will immediately yield phi of EG is in fact E sub h, right? Cancel this, cancel that. What are we left with? Phi of G is equal to, phi of EG is equal to phi of h. Okay, we have another definition, sort of the range of a function. So we define phi sub capital G to be what? This would be the value of all phi of little g as G goes in the group G. So that set phi of G, that set is actually what's known as the range, right? It's just if you think of G as being the domain, you run through all the values in the domain, put them into the function, see what comes out, you gather them together, that's called the range. And so we have a theorem, if phi is a group homomorphism, then the range is a subgroup of H. So let me attempt to prove this. Well, G is a group, so G is not empty. So there's some element G. Maybe I'll stick with my notes. Some element X in G. Then if Y equals phi of X, Y is in the range. So the range is not the empty set. So what we're going to do is we want to do the two-step subgroup test. We want to seek to apply the two-step subgroup test. So we first take any two elements of the range, call them y and y prime, that are in the range. So that means there has to exist some x and x prime in G, in the domain, that takes, phi has to shoot x to one element of the, right, phi instead of y, has to shoot x to that element y, and phi has to shoot that other element x prime to y prime. And so what do we have? If we look at y times y prime, this would be phi of x times phi of x prime. But phi is a homomorphism, so that's phi of x times x prime. But x prime times x prime is in G. So this is an element of phi of capital G. Again, because a group closed on the product, x times x prime is in G. So we've done step one of the two-step. We've taken our non-empty set, and we've shown that it has the product of any two elements in this non-empty set is still in the set. Okay, now let's go back. Let's just take a single element. Forget about taking x, y, y prime. Take any y in the range. As before, there's some element in G that if you're in the range, you've got to come from the function's got to send something to you. So we have that equation. Okay, so what do we have? Let's look at, then if we look at phi of x inverse, so what would that be? Let's actually, let's look at phi of x inverse times y is phi of x inverse. Y, as we just saw, was phi of x. Phi is a homomorphism, so it would be x times x inverse. But that's just the identity in G. And we saw by that lemma, the identity in G, phi is going to send the identity of G to the identity in H. And so if we look at that equation, what can we conclude? So y inverse has to equal phi of x inverse. So in symbols, we can think about the inverse of that element, phi of x. Again, this is inverse of an element in H. Turns out to be what we get if we take the inverse of this element in G and plug it into the function. Again, did I move too quick to make that conclusion? Remember, if something times y takes you to the identity, that means something is the inverse of y. So the range is closed on the product. We've now just showed it's closed on the inverse. So by the two-step subgroup test, that set is a subgroup. Now let me actually get that result from that I've just stated. I'll state that as a corollary. This comes right out of the proof. I've already proved this, so I'm just going to state it. Just in symbols, what I put earlier. That basically, given a group homomorphism, then phi of x inverse is the same as phi of the inverse, or the inverse of phi of x. So we've actually proved that, right? That's right stated in there. And we now leave another definition. Given from G to into H, we define the kernel of phi to be everything in G that the function maps to the identity. And the theorem we're going to prove the kernel is a subgroup, not only a subgroup, so this is called the kernel. The kernel of the mapping. And it's abbreviated by KRE of that. So theorem if we have a group homomorphism then the kernel is a normal, not just any subgroup, but a normal subgroup of G. Yeah, so the map, we have to be careful where we live. The range, that was out in the H, so the range was a subgroup of H. The kernel involves elements that we stick into the function, so the kernel is a subset of G. We're going to prove it's a normal subgroup. So we'll show it's a subgroup, then we'll show it's normal. First, note that phi of EG is equal to EH. So the identity of G is in the kernel. Which means we have a non-empty set. Here we're going to try to do the one-step subgroup test. So let A and B be elements of the kernel of phi. So we need to show that phi times B inverse is in the kernel of phi. Sorry, A times B inverse is in the kernel of phi. Well then if I look at A times B inverse, this is phi of A times phi of B inverse. That's a property of homomorphisms. But phi of A is just, we'll just leave it for time being as phi of A. And phi of B inverse is the phi of B, the inverse of phi of B. So continuing on, from this put over here, maybe I'll just work down here. But A is in the kernel, so that means phi of A is the identity. And B is in the kernel, that means phi of B is the identity. But the inverse of the identity is just the identity. And the identity times the identity is just the identity. So what does this tell us? This tells us that phi of AB inverse is equal to AH, so let me pull that out here. And this is an element of the kernel of phi, so the kernel of phi is a subgroup. And to save space, I'm not going to write the kernel of phi is a subgroup. I'm going to write kernel phi using the subgroup sign. Now we have to show it's normal. Well, remember the definition of normal we initially gave as the left and the right cosets. Each left coset is determined by an element is the same as the right coset. But we also saw another definition, and that was what? To show this is a normal subgroup, so that's what that triangle means. We need to show for all G and G, G inverse times the kernel of phi times G inverse is a subset of the kernel of phi. So let's do that. Take any G and G, and what do I use here? A in the kernel. Then what will we have? We'll have phi of, well, let's trying to show this is in the kernel, so I'm trying to show, oh, here's an erasure, this is G inverse kernel phi G, right? Conjugation by G. So then phi of little g inverse AG. Let's see what that equals. Since it's a homomorphism, it preserves the product. So we have phi of G inverse, phi of A, phi of G. But what is phi of G inverse? That's phi of G, the inverse of that, and A is in the kernel. So phi of A is equal to the identity. And then G is just phi of G. But this H soaks up, so we have phi of G inverse times phi of G. And that's just the inverse of some element times that element, right? Inverse of something times that times something gives you the identity. So what the heck does that show? I think that shows if I take this element and stick it into phi for any G and G, for any A and H, I get the identity. That means that G inverse AG is in the kernel of phi. So, since that element's in the kernel, this is true. This holds for every A in the kernel. So, G inverse the kernel of phi is contained, times G is contained in the kernel of phi. And that again holds, what was special about G? Nothing, that holds for each group element. So the kernel is a normal subgroup. And later on we'll actually see how to go the other way, how to, not only is a kernel a normal subgroup, but given any normal subgroup, how we can construct a homomorphism for which that normal subgroup is exactly the kernel. So we may have introduced the concepts of one-to-one and onto very earlier. I think I may have used them in a couple of the counting arguments when we maybe wanted to count that the number of left cosets were the same as the number of right cosets. One counting argument to show two sets have the same number of elements you come up with a one-to-one onto mapping. So in general, what we say, a mapping from phi from G to H is onto if, well, let's get it on the element level. For any H and H, we can find at least one element G and G with phi of G equal to H. Or if we want to move up to the set level, what that really means, if you have a mapping from G into H, what would make it onto would be if the range of phi of G fills up all of H. Again, just a notion with this notation means we have a function from one set to another set. All this tells us is that each element phi of G has to be an element of H. It does not necessarily mean that every element in H has to come from a phi of G. But this does. And just a note, phi, if we look at from phi, and we just want to consider to the range, phi from G to phi of G, is always onto. So again, in general, a mapping from G to some other set H may not be onto. But if we narrow that set, if we look at just the mapping considered from G to its range, phi of G, then that's got to be onto, right? That's the definition of this set. Everything in this set is the image of something plugged into phi. So certainly, it's onto. Okay, so again, we'll look at some examples. We're going to show a little wider. We're going to look at the a group of the Heisenberg group again, and we're going to look at a homomorphism of that set. So let G be a Heisenberg group. That's got a 1 down diagonal. It's got an A, C, and a B. It's got 3 integers. And let H be the product group Z cross Z. So that's all A, comma, B for A, B, and Z. And we've looked at the product group so far. The way we multiply, recall, how would we multiply two of these? Change my notation, maybe make it A comma B and A comma B prime. The way you multiply them is you just combine A and B using the group operation. In the integer Z, the operation is addition. So your first component would be A plus A prime, and your second component would be B plus B prime. So how are we going to define it? We're going to define a typical element what we'll choose to do is we'll map it to A comma B. So C does not factor in this definition of this mapping. So we want to check that phi is a homomorphism. Why? Since, well, let's look at the product of two elements. So that's one element, and the second element, we might have an A prime, C prime. And we see when we multiply these matrices, what do we get? We get 1, A plus A prime, 0, 1, B plus B prime, 0, 0, 1, and we get some, not mess, but something, which is what, A B prime, or C plus C prime plus A B prime. And what does that equal to? Well, by the definition of my homomorphism, it's just this element comma this element, so it's A plus A prime, B plus B prime. But that's exactly how we would combine two elements in the group. Okay, maybe I should use plus notation just because it's an additive group. So so we've got a homomorphism, right? Multiply the matrices first, then stick them into the function. That gives you the same result as if, well, wait a minute, I'm not quite done yet. So I've got that. Let me look at the other side now individually. So this is equal to A plus B, which is equal to that. So let me put an end. If I multiply each one separately, so I take phi of this element, and I group operation, I combine it with that. This is just A comma B. This second element would be A comma B prime. So we can see, in one case, multiply first, stick into the function, I get A comma B plus A prime comma B prime. Stick into each function separately and then add multiply. Multiply loosely, in this case, is addition, because that is the group operation in the integers. In some sense, the group multiplication, if you will, of the integers is addition. And they both are equal. That is that. So we have a homomorphism. Is it onto? Certainly it's onto. Sometimes onto is a little bit, not tricky to prove, but sometimes when you prove something is onto, it doesn't almost seem like you did anything. But let's show that it's onto. Take any element. What would a typical element look like? A comma B in the product group of Z cross Z. Then if I want to look at phi of 1, A, I put a 0 here, 1, 0, might as well use 0, doesn't matter, use 1. Remember, the definition of onto, it's not particular, it just says you have to find some x that when you put into the function, it takes you to y. So if you think about this is your y value, your output, you want to input this matrix, and we get A comma B. And so that's enough to show phi is onto. Or in other words, if I look at the image, if I stick every matrix into this thing, I'll be able to get back every ordered pair of integers. What about the kernel? The kernel of phi is equal to what? Well, let's think about this. What is the identity? Remember, the identity in Z cross Z, the identity in a product group is the identity in one, comma the identity in the other. This group's the same, Z, the identity in Z under addition is 0. So we want to end up with 0, comma 0. So I need to have a 0 here. I need to have a 0 here. And what do I need to have here? Anything. So we can just put a C here. So that is what the kernel is. Note the identity in the product group so why is that the case? I put some more details in the notes. Certainly, if I look at phi of this group, phi of anything in this form is just going to be 0, comma 0. So that tells us anything in this set is inside the kernel. So if we think about double containment, that basically shows me that this set is inside the kernel. But now if I take any typical element that's going to be in the kernel, what does that tell us? That tells us, well, when I plug this in, I have to end up with 0, comma 0. So, what is phi of that element? That would just be A, comma B has to equal 0, comma 0. So A equals 0, and also B has to equal 0. And that gives us the other containment, right? That tells us that any element in the kernel, like this, really needs to have A and B equal to 0. So it's going to be exactly a matrix of this form. So we'll stop here briefly, and we'll pick this up very shortly to continue on with the some more properties of homomorphisms.